Hello everyone, I'm Suvrat and today we'll be discussing CodeChef Starters 213. So I think I'm audible. So let's start with the discussion. So problem is number 4 please. An array B of length m is said to be good if no two elements from different indices sum to 4. That is, B is good if for every pair I, j satisfying 1 less than equal to I less than j less than equal to m, we have bi plus bj not equal to 4. You are given an array A of length n such that AI is from 1 to 3 for each index I. You would like to make this a good array. To achieve this, you can repetitively choose a single element of A and delete it. What's the minimum number of decisions needed to make a good array? And the constraints for this problem are there are 1000 test cases and n is still 100. So I think O of n square would work. Complexity up till O of n square will work. So problem A, basically you are given an array A where each element AI is from 1 till 3 and we need to find out the minimum number of elements to be deleted so that no such pair I, j where AI plus AJ equal to 4 exists in the array. So basically we need to find out the minimum number of elements that we need to delete such that there is no pair whose sum is 4 in the array. So let's see the test cases. Test case 1 is 1, 2, 2. So we can see that these two will form a 4 because 2 plus 2 is 4. So we need to remove one of these and hence the minimum number of deletions would be 1 for this test case. Then the next test case is 1, 1, which has 0 deletions because sum 4 is already not possible. Then we have 2, 3, 1. 2, 3, 1. Here we can see that 3 and 1 are forming a 4. So we'll need to delete this. And the answer would be 1 again. Then we have 2, 3, 1, 3, 2. 2, 3, 1, 3, 2. So we can see that these 2's form 4. So we'll need to delete one of them. So we can delete this. And then we see that one with this 3 or this 3 will also form a 4. So we need to either remove all the 1's or we need to remove all the 3's. So basically it is more optimal to remove all the 1's since we need to do minimum number of deletions. So 2 plus 1 plus 1, there will be 2 deletions in this test case. So basically observations would be what are the ways to form 4? Either there will be 2 plus 2 equal to 4 or there will be 3 plus 1 equals to 4. So due to there only being these two ways to form a 4, so one statement is we can have a maximum of 1, 2 in the array. There cannot be more than 1 2's in the array, and we can only have 1's or 3's in the array. Both cannot be. So basically if there are 1's and 3's both in the array, then we'll need to remove either one of those two. So what we can do is simply let's first satisfy this condition, so we need to remove either all the ones or all the threes from the array if both of them exist. So what we can do is we can remove minimum number of 1 comma 3. Let's just assume that 1 is the count of ones in the array and 3 is the count of threes in the array. So minimum of these two must be removed, and then because of this condition that we can only have 1 2 in the array maximum, so what we can do is maximum of 0 comma 2 minus 1. So this is not, this is 0 and 2 is the count of 2's in the array. So 2 minus 1 will be, we will need to remove all the 2 except 1. And if the number of 2's is 0, then we don't have to remove, and in that case 0 will be removed. So minimum of 1 comma 3 and maximum of 0 comma 2 minus 1 must be removed, and this will be the answer of the array. So to use this, we will need to calculate 1, 3 and 2 from the array. So we can do that in a simple for loop, and just if ai is 1, then simply 1 plus plus, and similarly 2 plus plus and 3 plus plus. So we can in one loop of O of n calculate 1, 2 and 3, and then the calculation of our answer would simply be O of 1. So overall time complexity used will be O of n. I'll show you guys the code. So basically vector v, and then I take input vector v, then 1, 2 and 3. Then using a for loop, I calculate the number of 1, 2 and 3, and then the answer is simply maximum of 0 comma 2 minus 1 and minimum of 1 and 3. So that was the solution for problem A. If you guys have any doubts, you can ask, or I'll move forward. Move forward. Okay, so how to improve in CP? Just consistently give contests and upsolve. There are no secrets. So let's move on to the next problem. So the next problem is separation. You are given an array A of length n as well as an integer x. X is said to be separated if there exists at least one index I such that ai is less than I and ai plus 1 is greater than x. ai is less than x and ai plus 1 is greater than x, or ai is greater than x and ai plus 1 is less than x. That is, x is said to be separated if A contains a pair of adjacent elements with one of them being strictly less than x and the other being strictly larger than x. You can freely rearrange the elements of A however you like. Is it possible to make x not separated? And the constraints for this is n is till 2e5 and the sum of n over all test cases does not exceed 2e5, and ai and x are both till 1e9, so expected time complexity should be less than equal to O of log n log n, because sum of n is constrained till 2e5, so O of n log n will pass. So problem B. Here in this problem we are given an array A and an integer x, and basically we need to tell if the array A is separated or not. So the definition for separated is if there exists an adjacent pair ai and ai plus 1 such that 1 is less than x and 1 is greater than x. So basically, if there exist two adjacent elements such that one of them is less than x and one of them is greater than x, then x is separated. So we can freely rearrange the elements of A however we like, and we need to tell if it is possible to make x not separated. Not separated means there should not be any pair where one is less than x and one is greater than x. So let's see the test cases. The first test case is 441524. So 441524. So this is n and this is x. So to solve the test case, the first thing we notice is that there is all the numbers less than x and all the numbers greater than x are have identical meaning in this specific problem. Basically, any number greater than x holds the same value for the problem. So let's since we can rearrange the element, let's try to treat every number less than x and every number greater than x as the same. So here we have 1 and 2 which are less than x, 5 which is greater than x, and 4 which is equal to x. So we have 1, 2, we have 5, and we have 4. And we need to rearrange these numbers such that the array is not separated. So the array should not be separated, right? So if we place the smaller numbers together, these numbers will not cause any problem since they are both less than x. So array will not be separated. But if I place 5 next to them, then due to this pair, the array will become separated because this is less than 4 and this is greater than 4. So what we need to do is we need to separate out the smaller and the larger numbers. So what we can do, we can place a 4 in between so that now these two are less than 4 both, and these two here, one is equal to 4, and our condition for separated was strictly less than and strictly greater than. So here we have 4 which is equal to x. So again this pair is also okay, and again this pair is also okay. So one quick observation that we can make from this test case is if we have an element equal to x in the array, then we can basically follow the exact same pattern that we followed in this test case and form the output array as all the small elements, then we have whichever ai was equal to x, let's say that ai is equal to x, and then all the large elements, all the greater than x elements, and here we have all the less than x elements. So if we follow this pattern, we first place all the less than x elements, then ai which is apparently x, and all the greater than x elements, then here we will have no adjacent pair where one is greater than and one is smaller, and here also we will not have a pair where one is strictly smaller and one is strictly greater, and these two pairs will also be not because ai is equal to x. So in this case the answer is yes. Answer will be yes in this case. Let's move on. So 1524, now we are given that x is equal to 3 and we are seeing that there is no 3 present in the array. So let's see this test case now. So we have x equal to 3 and the array is 1, 5, 2 and 4. So again 1 and 2 kind of have the same identical value, and 4 and 5 also are identical in nature. So no matter what I do, I cannot separate out these elements from these elements, right? Because let's try every possible combination. 1 5 1 2 4 5. Even if I try to put these numbers in between here, then again there is a problem. So these numbers have to be separated, but the boundaries will always come near adjacent to each other, so that will cause a problem. So no matter what we do, we cannot rearrange them. So the answer for this test case will be no. Then the next test case is 3 6 7 1 3. So x is given as 9 and 3 6 7 1 3. So we notice that all the elements here are less than 9. So what we can do, we can just keep the array same, and there will be no pair where an element is greater than x, because there are no elements present in A which are greater than x. So the answer for this test case will be yes. So again, obvious observations that we can make from these two test cases. Observation 2 will be that from this test case, we can see that if all elements are less than x or greater than x, then the answer is yes. Yes, because there will not be any adjacent pair where one is greater than x and one is less than x. And the final observation needed to solve this question is, so if we have elements less than x as well as elements greater than x, and there is no element equal to x, the answer is no. Why? Because there will be no way to separate out each less than x element from each greater than x element. We cannot do that. There will be at least one adjacent pair where one is less than x and one is greater than x. So in this case, the answer is no. Or so basically, we can just check for these two conditions, and if both of these conditions are false, then simply the answer will be no, else the answer will be yes. So now how can we check? So we can take input the array and sort the array. Now if we sort the array, then if v of 0 is greater than x, then that means since the smallest element is greater than x, then all the elements in the array would be greater than x. Or v of n minus 1 is less than x. So if the largest element is less than x, then all elements would be less than x. Or we can see that if there is any element v of I equal to x, so in these three cases the answer will be yes, else no. So we can sort the array in O of n log n. Then these two conditions would be simply O of 1, and then we can also check for this condition in O of n. So overall time complexity required will be O of n log n. So I'll show you guys the code. So I take input the vector v, then I sort the vector v, then bool check is equal to false is for the third condition, where I am checking if there is an element present which is equal to x, or so check, or if all the elements are greater than x, or if all the elements are less than x, then yes, else the answer no. So that was the solution for problem B. If you guys have any doubts, you can ask. Able to solve 5 problems in div 4. Problem 1, 2, 3 were same from div 2. Okay, we'll be discussing till E, problem 5 in div 2. Fourth one was actually really good. Yep, that is a good problem. So I don't think you guys have any doubts. Let's move on to the next problem. So chef and string. Chef has recently joined Exxon, a member of the V. So I don't think this is relevant. Chef string denoted A is very large. So you are instead given a smaller string S of length n and a positive integer k, where chef string is represented by the string A is equal to S plus S plus S k times, where plus denotes string concatenation. So if S is xn and k is 3, the chef's actual string is xn xn xn. Note that the length of A is exactly n into k. So as a sign of respect for his club, chef refuses to have the letter I present in the string. So chef will replace every occurrence of I in his string with any other uppercase English letter of his choice. Note that different occurrences of I may be replaced with different characters. For example, the string IAIA can be turned into BACA or EAEA or Java or many other examples. Chef defines the score of a string to be the number of adjacent characters that are equal. Formally, the score of A equals the number of indices I such that AI is equal to AI plus 1. Find the maximum possible score chef's string can attain after replacing every occurrence of I with some other letter. And the constraints for this problem are n is given till 5e5 and k is given till 1e9 and s contains uppercase English letters only. The sum of n over all test cases does not exceed 5e5. So the expected time complexity would be less than equal to O of n log n because sum of n is constrained till 5e5. So problem C. So we are given a string A which is nothing but s plus s plus s k times, and the length of s is 5e5. Yep. And so basically what we can do, we can convert every I in the string s to any other character. And we need to find the maximum number of indices such that AI is equal to AI plus 1. Maximum number of indices such that AI is equal to AI plus 1. So that's it. Let's see the test cases. So the first test case is IAI, and k is equal to 2. So basically, since k is equal to 2, the final string A would look like IAI. This A is confusing. So let's just write it like this only, IAI and then IAI. So since apart from I, there is only letter A present in the string, so we can already guess that every I we will change every I with A only so that maximum adjacent pairs are same. So let's just change this array into AAA and then AAA. So the number of indices would be 1, 2, 3, 4 and 5. So the answer for this test case is 5. And then the next test case is CILLI and k is equal to 1. So CILLI I, L, L, I, and K is equal to 1. So now we need to make decisions for these two I. So we obviously can see that obviously this I would be either C or L, and this I would be just L only, because K is equal to 1. So this is the final string A, and if we put this I any other letter other than C or L, then that is obviously a very bad decision. So we will either place C or place L, and actually it does not matter either we place C or we place L, because let's try to take both the cases and see what's the difference. And for this I will obviously place only L only. So C, let's first place C, L, 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 and other case would be C, L, 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 L. So in this case we have one pair, two pair, and three pairs, and in this case again we have one pair, two pair, and three pair. So from both the answer is 3 only. So we can see that if we had placed C here, the pair forms like this, and if we had placed L here, the pair forms like this, and the answer doesn't really change, because literally if we place C, then the answer is nothing but 1 plus the answer of this string. And if we place L here, then again answer is nothing but 1 plus the answer of this string. So the answers of this string would be identical, so it does not really matter if we place C or we place L. So one observation we can do from this is, if we have a case like this, x1 we are given some alphabet which is not equal to I, and then I, and then x2 again, let me just, if we have this kind of sequence in the string x1 I x2, and x1 comma x2 are both not equal to I, so we can just place I as x1 or I as x2. It does not really matter. We can place I as any of the alphabet x1 or x2. Still you will get the correct answer. So let's just decide a rule here that we will always place I is equal to x1, because we need to solve the question. So we need to follow one strategy. So let's just place I as x1. We could also place I as x2. That would also give the correct answer. So let's move on to the next test case. Now we have again CILLI with K is equal to 3. So CILLI and CILLI and CILLI. So we can see that the observation we just now made, we can make use of that and solve this test case, because every I other than this I is following our rule. So let's just make this as C and just put C, L, L, then L, then C, C, then L, 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 then C, C, then L, L. And obviously for this I, the optimal would be L only. So we have one pair, two pair, three pair, four pair, five pair, six pair. So the answer for this is, okay, I didn't count this, and this. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pairs. So the next test case is exunite, and K is equal to 2. So it will look like this: exunite and exunite. So again, we have the observation that we made. We can again make use of that, and just this string will become exunte and exunte. So this, and so number of adjacent same would be 1, 2, and 3. So the answer for this test case is 3. Then we have all i's. So I, and K is some 10 to the power, I don't know what is this, 10 to the power 9, I think. Let's just take 10 to the power 9. And this is 1, 1, 1, 1, 1. I. So obviously we can just change this I to any same character A, because every single character would be same, so all adjacent pairs would be good pairs, so we will have to count all the pairs. So actually in case like this, the answer would be simply number of all pairs would be the answer. So n into k minus 1, where n is the length of string, so n into k minus 1 would be the answer in these types of cases. Because I can take, let's take k is equal to 2 for this test case only, so the string will look like, so we can see that every single index will be counted except the last index. We accept this index, this one, this one, this one, this one, this one, all of these would be counted except the last, because there is no element after this. So except this, everyone will be counted, so that would be n into k minus 1. So this is another observation. We can say that if all the elements are I, then answer is n into k minus 1. N is equal to length of string s. So this, and now let's see the next test case. So I think, so let's just shorten this test case and write it like this. I, then only EE is there. So let's just write it like this only. I, then L, then EE, and then we can just write T. And then how many I's are there? 6. Because obviously even if we do concatenation, all these characters will have the same neighbors, because for all of them the neighbors are fixed only, right? So obviously apart from EE, no one will be ever forming a pair, adjacent good pair. So we can just shorten it like this. Although we'll not be doing this while coding, or we will not use this as a main part of our logic. I'm just doing this so that we can understand this test case better. We can solve this better, because it would be hard to write this again and again. So this and k is equal to 3. So since k is equal to 3, so let's just write this string 3 times. So for this first I, we can see that it will become L only. We can see that it will become L only. So let's fix this as L. So the string becomes LEET. And we can see that for these I's, they will become T only, because there is no letter after them. So they'll become T only. So T, 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 T. So these characters are fixed, right? So we have these I in between T and I. So what we can do? We have this as our problem currently, that we have a T, these I's, we have a T, and we have 7 I's in between. 1, 2, 3, 4, 5, 6, 7, and we have an L. So what do we need to do in this case? So basically we can again follow the pattern that we found in the first observation, that if we have xi, then x1, then I, then x2, then we can always place xi is equal to x1. Here we found this for the case where x1 and x2 were not equal to I. But we don't have a similar kind of situation here, because x1 is t but x2 is I here. So, but I'm saying that again, placing them all as T would be our best choice here, because let's say that we place this I as T, then we will be forming this pair. Now, if we place this I as anything other than T, then we will be missing out on this pair. So basically, again, we can just put them as T and we will get the optimal value, because the maximum number of pairs, what are the maximum number of pairs that we can form in this? Let's think about that. So let's say that this is a pair, this is also 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 a pair. So if these all are pair, that means all of them were T only, right? So this cannot be a pair. This cannot be a pair. It must not be a pair. So the maximum number of pairs that we can make is total length, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 1 is the maximum number of pairs that we can make. We will never be, sorry, actually not 9 minus 1. 1, 2, 3, 4, 5, 6, 7, 8 minus 1. Last actually never forms a pair, right? So 8 minus 1 is the maximum number of pairs that we can form, because if we, there will be at least one out of these 8 which will not form a pair, because here there is L. If we want this to form a pair, we will have to place L. Only then this will form a pair. But if we place L here, then for this to form a pair, we will have to place L. Then for this to form a pair, we'll have to place L. Then for this to form a pair, we'll have to place L. And if we place L here, then this will not form a pair. And if we try to place elements from the left side, then again for this to form a pair, we'll have to place a T, 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 and then T. So again, this will not form a pair. So the maximum number of pairs that we can form here would be corresponding to two cases. Either we can place all L's here, or we can place all T's here. There is one more I, no, actually, okay. Number of I's are correct. So again, we kind of still follow that rule. We can extend this rule to multiple I's. So if we have a situation like this, x1, then I, x2, then we can simply replace it by x1, 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 and then x2. So let's just follow that strategy here again. So this will become T, 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 and again LEET, then again all T's here, and this. So let's count the number of pairs now. 1, 2, 3, 4, 5, 6, 7, 8, and 9. 1, 2, 3, 4, 5, 6, 7, and I have counted here 1, 2, 3, 4, 5, 6, 7. Okay. So 1, 2, 3, 9 here, 9 till here, then 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So the answer for this test case is 24. So what strategies we have followed till now? We have used x1, I x1, we just replaced by, or actually let's just write the generalized one. X1, I, x2, we replace this by x1, x1, x1 till x2. So this thing, and since we are replacing the i's with the last character, last non-I character towards the left, so what happens when we have i's in the beginning? We saw that we will just replace them by the next character that we have. So let's take a test case to understand this better. If we had like this I, L, E, and T, then I, and for any x equal to, let's say, 3, these 4 I will become T, and these 3 I will become L, because since we don't have an element before them, we will just use the element after them, and here we will use the element before them. So now we can write this as this, and again let's just concatenate. Let's just take x equal to 2. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pairs here, right? Now, what if we had done it the original way that we were doing before? So, according to our strategy, we will be placing else here. And for all these I, we will be placing T. So, T, 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 T. And then L, E, E, T. And then we will be placing T's here. So we see that this string is different from this string. Why? Because first the number of L's in the starting, they are the same. The T's in the ending, they are the same. But in between, we have these T, 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 T and L, L, L. But here we have done 7 all T's. So actually we can say that it doesn't matter that if we have a case like this T, L, I, then we can see that if we place all of them as T, in this case the number of pairs would be 1, 2, 3, 4, 5, 6, and if we place all of them as L, then again 6, and if we place some of them as T and some of them as L, then again the answer would be 6 only. Because simply we can just divide this into two things, and we can just take the left value for these ones and the right value for these ones, and because of our above result we will be getting the optimal result. So it doesn't matter. What we can do is we can decide for one string, we can decide for the string S that a value of all the i's, and then just concatenate that string and you will get the perfect answer, maximum answer. So now how do we calculate the answer from string S to the concatenation of string S? Because we can't generate the concatenation like this and then count it. So basically we will be recounting a lot of adjacent pairs, right? So we don't need to recount them. So what we can do, we can say that if we know the answer for S, so let's say S is L, L, E, E, A, and again L. So S is this and K is equal to 5, let's say that. So the answer for S is 1, 2 and 3. We can see that the answer for S is 3. So when we concatenate this, we will be getting these pairs, we will be counting these pairs in every occurrence of S. We will again count these pairs, right? So let's denote this as CT. So CT into 5, these pairs would be counted, and then there will be some more pairs, this pair and this pair and this pair, basically the last element of the first S and the first element of the next S. So we need to count this pair as also. So what we can do is so this pair will first of all occur k minus 1 times, so 5 minus 1 times, and then if these two are equal, then we will be adding 1 for these pairs. So we can just say that S of 0 equal to S of n minus 1. If the first element is equal to the last element, then we will count it k minus 1 times and CT into 5, where CT is the answer for S. So this will be the total answer, and the strategy we can follow is replace every I by the last character which was not I. And for i's in the beginning, replace them by the next non-I. So we can do this. We can perform this in easily in O of n, and then we can count the number of pairs, which will be Ct, and then we can just use this formula Ct into k plus k minus 1 into s of 0 equal to s of n minus 1. Simply this. So I'll show you guys the code for this. So I take input the string s. So I'll maintain a character last, which I will initialize with the first non-I character in S. The first non-I, basically I'll run a for loop from 0 to n minus 1, and if Si is not equal to I will just store that in the last and break. So this last will mean the for i's in the beginning, replace them by the next non-I. So this last denotes the next non-I character. So what I can do is I can start iterating in the string S, and if Si was equal to I, then I just replace Si by last. Else if Si was not equal to I, then I can just update my Si last to Si. So in this way, all the i's in the beginning will be updated by the next non-I character, and then after that every I will be replaced by the last non-I character which was before them. So we can run this for loop, and then val is the ct is val. So we can just run a for loop and check if Si is equal to Si plus 1, then val plus plus, then val into k plus k minus 1 into Sn minus 1 equal to S0, and then see out val. And also one more case, that if the last turns out to be underscore, that means this for loop didn't find any character which was not equal to I. So that means all the characters in the string are I. So in this case, the answer is n into k minus 1. So this was the solution for problem C. If you guys have any doubts, you can ask. You missed one EE pair, answer comes as 26. Where did I miss that? No. Oh, in this, okay. Still the answer is 24 only, answer is not 26. You can count, answer is 24 only. Yes, I think I missed this while counting. Okay, so if you guys have any doubts, you can ask. I'll wait for a minute and then we'll move on to the next problem. Okay, so I don't think you guys have any problems. So let's move on to the next problem. So so this problem is mean difference. This is the easy version of the problem. So for an array B of length m, we define the following. Average B is the average of B rounded down formally. Average B is nothing but B1 plus B2 till Bm upon m, where x denotes the largest non-integer exceeding x, also called the floor function. F of B is the maximum difference between an element of B and average B, that is f of B is equal to maximum of I equal to m, I equal to 1 till m, Bi minus average of B, and mod x denotes the absolute value of x. So you are given an array A of length n, compute the maximum value of f of s across all non-empty subsequences s of A. So n is given till 2e5 and sum of n again is given not won't exceed 2e5, so expected time complexity would be n log n, I think less than equal to n log n. So problem D. So basically we have this definition of f of B, which is nothing but I is equal to 1 till m, not summation, max of I is equal to 1 till n, and Bi minus, let's denote average of Bi like this. So B bar is nothing but B1 plus B2 till Bm, m here also, upon m, and floor of this. So this is B bar, and we need to find f of B. So in the given problem, compute maximum value of f of s across all non-empty subsequences s of A. So we need to find maximum value of f of s where s is a subsequence of A. So before I move on to the test cases, one very quick thing that you should be noticing when you see this function is that here we are taking max of I is equal to 1 till m Bi minus B average. So B average is nothing but like, let's say on a number line, let's say there is a number line and we select these numbers. So B bar is nothing but an average of all these numbers. So it would lie somewhere in between these two numbers, right? And okay, we have an absolute also here, absolute. So maximum value of absolute of Bi minus B average would be always either from the minimum element or from the maximum element, because if we take an element smaller than the maximum element, then this difference and this difference, obviously this difference will be greater, right? And similarly we can say that this difference and this difference will always be greater. So either this maximum value will come from the element smallest element or it will come from the largest element. So we can uh, reduce this function to a very to a simpler function, which is f of b is equal to maximum of, we can say that, b average minus b low, comma b high minus b average. So b high is the maximum element in b and bl is the lowest element in b. So we have found out this. So now our problem changes to maximum of s, and this f of s we can write as max of b bar s bar minus sl, comma sh minus s bar, and this we can obviously change to the maximum s bar minus sl, comma maximum for all sh minus s bar, and the maximum of this. So answer. So this is a pretty quick mathematical analysis that you should do and should be able to see after viewing the question. So we can kind of dilute our problem to this problem. This is a very easy looking problem now compared to the last problem. We see that now we need to just calculate these two values separately. We don't have any functions like this that we need to maximize, or this function or this function. Now we can just simply for all subsequents calculate the maximum value of s bar minus l sl, and for all subsequents calculate the maximum value of sh minus s bar, and then take the maximum of both of these two numbers. So let me write this equation formally in words. We can find maximum value of s bar minus sl for all subsequences of s, and maximum value of sh minus s bar for all subsequences of a. Subsequences of a, and maximum of these two values will be the answer. Maximum of these two value will be the answer. So let's try focusing on finding these two values. So let's now see the test cases first. So the first test case is 8591. 8591. So we need to find let's try to do this. Let's just take all the subsequences. Let's just do brute force and let's take all the subsequences. So we have 1598. We have these four. Then we have 15, 19, 18, 59 and 58, and 98. So we have these, and then we have more. We have 159, we have 158. So 159, 158. We have not taken 9 once, we have not taken 8 once. So we will not take 1, 8 and 9 and 8, 5, 9. So these three, and the last is 1, 5, 8 and 9. So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So obviously, yep, 2 into 2 into 2 into 2, 16, and minus the case where we don't take any element. So these 15 cases we need to solve. So we can see that for the one length subsequences, simply BL is equal to B average and B high is also equal to B average. So we don't really need to do much here. Answers will be just 0, 0, 0 and 0 for these four. Then we can see here the average is 3. So for this, the answer will be 2. Here we see the average is 5. 5 minus 1, 4. 9 minus 5, 4. Again 4. So here average is 8 plus 1, 9 upon 2, which is 4. Because we are doing floor division. So 4, the answer here will be 4. 8 minus 4 is 4 because. Here the answer will be 9 plus 5, 14, 7. So 2. Here it will be 13 by 2, 6. So again 2. Here 17 by 2, 8, 1. When we take all four elements, 17 and 522, 123, 23 by 4 is 7, 6, 5. 23 by 4 is 5. So for this, it will be 4. Then 159, 15, 7 is the middle. So the 6, I think 6, 14 plus 1, 15 upon 2 is 6. 159 is 6 plus 9, 15 upon 2, which is 7. And 7 minus 1 is 6, right? So how come the answer is 5? Um, 10. Oh, sorry, it is 5. My bad. My bad. It is 5. And so for this, it will be 4. Here, 9 plus 5, 14. 14 upon 3 is 2. So here it will be 14 upon 3 is 2. How come 2 is average? 8 plus 5 plus 1 upon 3. 13 plus 1, 14 upon 3 is 4. Sorry, my bad. I'm 4. So here it will be 4. 9 plus 8, 17 plus 1, 18 upon 3, 6. So here it will be 5. And 14 plus 8, 22 upon 3, 7. So here will be 2. So we can see that 5 comes out to be the maximum number. But obviously, if we follow this process while solving, so the number of subsets will be O of 2 to the power n, right? And then we need to process each subset as well. That will take O of n complexity. So this is a pretty high complexity. We won't be able to solve it like this. So what observation can we make when we see this? That we can see that 158 and 189. Why did 189 give us a better answer? Why did 189 give us a better answer? Because obviously we can see that the distribution is like this. Here 1, 5 and 8 look like this, while 189 looked like this. 1, 8 and 9 look like this. So obviously if we compare the B average minus B low values, so here the B average would be somewhere here, and in this case the B average would be somewhere here. So we can see that B average is far more, B average minus BL is far better in this case. So we need to have bigger values. So we can think of a strategy to find the maximum value of S average minus SL based on this fact. Because obviously taking 5 over 9 was not a good choice, right? Let's say that we have fixed the first element as 1. Then obviously the next element we should add to our set is 9. And after that we should add to our set is 8. And only after that we should think about adding 5. Because adding greater numbers will increase our average. And since we have already included 1, the below is kind of fixed. So let's, instead of just following our intuition here, let's try to involve a bit of maths. So let's just focus on finding out this value, maximum of B average minus BL. Let's focus on finding out this value. So we just now saw that having just one small values and the other values large, that kind of shifts the average towards the large number, and B average minus B low increases. So we can kind of follow that strategy, and let's test it to see if it is true or not. Let's test it mathematically. So let's say that I have an array B1 plus B2 till Bm upon M. So this is the B average, and let's say that the smallest number out of all these is B1 only. So let's actually, okay. So what if I have another number X which is smaller than B1 and try to insert it into this set? Actually what I'm doing is try to replace B1 and X. So how do I say this more formally? Let's say that I had an array which was 1, 2, 4, 6, 8. So what I'm currently doing is I am trying to see if actually for the optimal value of B average minus BL, will BL be always equal to 1 or actually the smallest number. So to prove my intuition upon this, that BL will always be the smallest number in the array, basically I am saying that I will always include 1 and then I will include the higher numbers 6 and 8 for example. So I'm trying to prove that. So how am I proving that? What we can do, we can simply, let's assume that we take a subset S which does not contain M, and M here denotes the smallest value. So if we take a set S which does not contain M, what we can do, we can calculate its value, which will be B1 plus B2 till Bm upon M minus, let's say the smallest value in this set was B1. So this, now I am saying that I can always replace this smallest value with M and always get a better answer. So if I am able to prove this, then that means the answer will always improve upon replacing the smallest element with M. So basically the final result will always correspond to B bar minus M only, and we will always take M in our set, in our subsequence or set. So what we can do, let's compare both values. It is pretty easy to compare them. So we have one quantity this upon M minus B1, and we have another quantity M plus B2 plus B3 till Bm upon capital M. So this small m is the smallest number of the array and capital M is the total number of elements taken in the subsequence minus M. So we need to compare these two quantities. Also floor, that is also important. So floor. So we can use one property of floor. We can basically move this B1 inside the floor and this M inside the floor. So B1 plus B2 till Bm upon M plus minus B1 and M plus B2 plus B3 till Bm upon capital M minus small m. So it is pretty easy to prove this property, and let's not break the flow right now, and I'll prove that in the end. It will take literally 1 second. So let's just continue, and for now, if you guys have doubts regarding how did I move this inside the floor function, so just assume it is true for now. So we have these two values, so we can just take LCM. Then we will have B1 plus B2 till Bm minus capital M B1 upon capital M floor, and this value as M plus B2 plus B3 till Bm minus capital M into M upon capital M. So we need to compare these two numbers, and we can obviously see that all of these numbers are common, right? And the denominator is also common. Denominator is also common in both the cases. And we know that B1 is greater than M. So here we have B1 minus M into B1, which is nothing but B1 into 1 minus M, which will be less than M into 1 minus M, because 1 minus M is less than equal to 0 quantity, because M is greater than equal to 1. M is the size, right? So M is greater than equal to 1. So this is a negative quantity. So since we are multiplying a negative quantity on both sides of the inequality will change. So this becomes less than, and then we can just add this to both the sides and divide by M. So it becomes exactly this, B1 plus B2 till Bm minus MB1 upon M, and we can also take the floor on both sides. So if we take a floor, this inequality changes to less than equal to, and we simply have M plus B2 plus till Bm minus capital M into M upon capital M floor. So this proves that if I replace B1 with M of any set, the answer will always increase for that given subsequence. So our final optimal answer will always have the smallest integer in the array. Will always have that as one of its element. So we kind of now transformed this problem into this problem, maximum of B bar minus M, where B bar is the average of a set which necessarily have M as its element. This thing. So this is kind of the new problem, and now I can just show you how that let's just take this B1 by M floor of this plus X. So this is pretty much equal to B by M plus X if X is an integer. How? Because let's just write B by M as I plus F. So I is the integer and F is the fractional part. So floor division of this would be nothing but I. So this will be I plus X, and about this can be written as I plus F plus X, and again the floor of this would be I plus X. So both of these quantities are same if X is an integer. So that's how I moved B1 inside this floor function. So upon comparing that, so now the new problem that we got is maximum of B bar minus M for B belongs to where B is a subsequence of A containing M, small m. So since M is a constant here, we can write this function as maximum of B bar minus M. So now our problem, which was sounding very difficult in the beginning, now it will sound quite easy. We need to find maximum average of a subsequence containing M. That's it. We just need to find the maximum average of a subsequence containing M, and that is nothing but maximum B bar, and simply minus M would be the answer of this function, which is the first sub-problem, which is the sub-problem that we broke our question into. So now how do we find the maximum average of a subsequence containing M? We can use a pretty standard, or we can say pretty obvious observation. Let's say we have a collection of some numbers. We have a collection of numbers A1, A2, A3, A4, and so on till AN. So the average of these numbers, let's say that A bar is the average. So if we add a number X in this sequence, then if X is greater than A bar, then average will increase. Else if X is less than equal to A, average will decrease or remain constant. So we can prove it pretty easily. Initially the average is A bar, and then finally it will become A bar into N plus X upon N plus 1. So X can be written as A bar plus T. So where if T is negative, then X is less than A bar. If T is positive, then X is greater than A bar. So this will simply become A bar N plus 1 plus T upon N plus 1. So this becomes A bar plus t upon n plus 1. So if t is positive, then average increases. If t is negative, then average decreases. So if t is positive, x is greater than a bar. If t is negative, x is less than or equal to a bar. So we use this kind of observation to find the subsequence which has the maximum average. So what we can do is we can follow this strategy. We can maintain a set which has the element m, and we can maintain a set which has every other element in the array and sort it. And what we can see is we can try to add the largest element here and update the average of this set, and then do the same for the second largest. Now if this second largest is greater than the updated average, we will add it. Then again we see that if the third largest is greater than the updated average, we will add it, and we will do it till we can. At some point the numbers will be smaller than the average of this, so adding numbers after that will not increase the average of this set. So we would have found the maximum average of this set. So let me show you guys by dry running on a test case. So let's just take the first test case only, 8591. So initially we will take our set as 1, and we have 5, 8 and 9 as the elements that we can add to this set. So obviously current average is 1. So we see that this 9 is greater than the current average 1. So we will add this into our set. So our set becomes 1, 9. Now the current average is 5 by 2, 10, 10 by 2, 5. So we see that 8 is greater than our current average. So we add it in our set. So our average becomes 189. The set becomes 189. So the average of this is 17, 118, 18 by 3, 6. So we see that 5 is less than 6. So if we add 5, according to our property this, the average will reduce. But we need to find the maximum average of a subsequence containing this 1. So this will be the corresponding subsequence, and the maximum average would be b bar is equal to 6, and 6 minus 1 would be the value of maximum of b bar minus bl. So which was our problem initially, this thing. So we have found the solution for this. Now we have to find the solution for maximum of sh minus s bar. So we have this problem now, maximum of sh minus s bar. So symmetrically, just because we saw that SL was small m in the last problem, we can symmetrically say that SH will be equal to capital M, which is the maximum element of the array. So max of M minus S bar. So this will become simply M minus minimum of S bar. So now we need to find the minimum average that we can get from a set containing the maximum element. So again, we can follow the same procedure. Let's take the initial set. Let's take the test case 1 only. 8591. 8591. So initially our set will contain just 9, and the elements that we can add to this set will be 1, 5 and 8. So obviously this time we will add elements smaller than our average because we need to reduce average. So currently our average is 9, and we see that 1 is smaller than the average. So we will just add 1. And now the average will become 9 plus 1, 10 by 2, 5. So the next element 5 is equal to the average. So there is no point in adding that. And 8 is also greater than the average. So that will increase our average. So 9 plus 1, 10 by 2, 5. So the answer for SH minus S bar in this case would become 4. So the maximum value of SH minus S bar in test case 1 is nothing but 4. And the answer for test case 1 will be maximum of 5, 4, which is 5. Now let's follow this second test case is obvious. We don't need to check for that. Let's do this in the third test case, 3, 9, 48, 8, 61. So 3, 9, 48, 8, 61. Let's first find S bar minus SL. So initially our set will contain 3. The elements we can add will contain 8, 9, 48, 61. We can add 61 obviously. So 3, 61 it will become. which has the average of 64 by 2, which is 32. Again, 48 is larger than that, so we can add it. So 3, 48, 61. And how much is that? 48 plus 61 is 109 plus 3, 112. And 112 upon 3 would be, let me do it real quick. 112 upon 3, 37. So obviously 9 is smaller than 37, so we won't be adding that since we need to maximize average. So average of this becomes, so this comes out to be the maximum average. So 37 minus 3, 34 is the value corresponding to this. Then for SH minus S bar, let's initialize our set with 61, and the remaining elements that we can add are 3, 8, 9, 48. So obviously we'll be able to add 3, then we will be able to add 8. So 61, 3, 8, and the average becomes 64 plus 8, 72 upon 3. 72 upon 3, 24. So we can add 9 also, since 9 is smaller than 24. So we will add 9. And then we cannot add 48. So this will be our final set. So the average of this is 61 plus 3 plus 8 plus 9 divided by 4, which is 20. And 61 minus 20 comes out to be 41. So answer for this test case is maximum of 41 comma, what did we get? 34, which is 41, which is correct. So we just, in this problem, we just need to maintain two multisets and just keep checking the maximum element. If it is greater than the average, we can add. And here we will check if the minimum element is less than average, we can add. So this will be implemented in O of n log n pretty easily. I'll show you guys the implementation. So I take input the vector v, then I sort the vector, and then I'll be finding the answer for the case of S bar minus SL. So this will be, first I'll maintain this multiset for taken elements, which will contain the smallest element, and left elements will contain all the other elements from I1 till n. And sum is the sum of the current multiset. So sum will initially be v of 0. So this while loop, so this is the greatest element in the left set. So if the greatest element is greater than the current average, average is sum upon size of the set. So if the greatest element is greater than that, we will just erase it from the multiset and add it into our sum. And we will just keep on doing it till we have an element which is smaller than average, or we have used up all the elements. And the first answer would be simply average minus the smallest element. And then we can follow similar procedure. We can add the highest element, sum is this. Then we can take from 0 to n minus 1 all the left elements. Then if the smallest element is less than average, we can add this in the taken and add this in the sum, and answer will become highest minus the average, sh minus s bar. So taking the maximum of both of those will be our final answer. This is O of n log n. So if you guys have any doubts, you can ask. Give some tips for how to identify the greedy will work or not. Generally, most of the greedies, you can prove it mathematically most of the times. Like how I did currently, you can follow your intuition and then see mathematically if your intuition was right or wrong. You can do that. Or in some case, there are pretty standard problems. Oh, sorry, I by mistake. So I think the live stream should be back now. I'm sorry for that. So basically, you can either try to prove you're greedy mathematically, or you can. There are pretty some common greedy problems which have proved solutions like potions. So if your problems fits into that kind of problem, you can use those greedy solutions. Or else, most of the time, it is quite difficult to prove a greedy solution. It is mostly your intuition. So, but I don't think in questions till D or E, you will find a solution that you cannot prove. Mostly those solutions could be proved either mathematically, or you can just prove that this will be the best answer possible. I did max of take one small element, then n minus one large element, take one big element, then n minus one small elements, but failed in hidden test cases. So basically, it is not necessary that you will take all the n minus one large elements. You you need to see till when you can keep adding those large elements. You will be adding those till your average increases, or you will add those small elements till your average decreases. When should we trust our intuition and when should we not? In my case, I always do trust my intuition. So basically, what I'll do is I'll read a problem, and whatever I intuition I get, I start basing my solution upon that. And if I believe that I'm taking too long, or I am not going anywhere, so at that point I stop myself and I start the question from basic. I don't just keep complicating my thought process, because generally the solutions are quite simple. You don't see a problem with a very complicated or overly difficult implementation solutions. Problems are not like that. Mostly the solution is always simple. So think simple. If you're thinking complicated, then you're probably not going in the right direction. I think intuition is the first step for a lot of people, and you will build that by solving a lot of problems. Like when you solve a lot of problems, see in you will see instantly after seeing a problem that what needs to be done, what is expected. Do I need to solve this mathematically, or do I need to think greedily, or there might be DP? So you kind of get that intuition. And I'm not saying that I'm right every time. I myself cannot solve many problems, and my intuition is wrong many times. So that's just you keep learning. So if you guys have any doubts, you can ask. I'll be back from washroom in a minute. You trust your intuition because you are experienced, but I'm a fresher. Sometimes my intuition is right and sometimes it is wrong. Um, since you are every time your intuition is wrong, you are basically adding that to your experience, right? So the next time you have slightly less chance of your intuition being wrong. So like, don't worry about that. You'll obviously improve if you keep practicing. There is no secret method that I can tell you. So I think I can move on to the next problem. So you maximum product walk. You are given a tree with n vertices. Vertex I has the integer ai written on it. It is guaranteed that ai not equal to 0. A walk in the tree is a sequence of vertices x1, x2 till xk such that there exists an edge between xi and xi plus 1 for each one from I till k. The length of such a walk is said to be k. Note that in particular it is allowed for vertices to repeat in a walk. The score of a walk is defined as follows. Start with p equal to 1, then for each I equal to 1, 2, 3 till k in order, update p by using the following rules. If vertex I has appeared before in the walk, do nothing. That is, each vertex must only be processed the first time it's seen. Otherwise, let w equal to a of xi be the value at the current vertex. Then if w is positive, multiply p by 2 to the power w. If w is negative, multiply p by minus 2 to the power minus w. The score of the walk is then the final value of p after all k vertices have been processed. Your task is to compute the maximum possible score of a walk in the tree. The walk can start and end at any vertex and have any positive length. In particular, it is allowed to start and end at the same vertex without moving. The answer can be large, so reported modulo this. And the constraints are n is from 2 till 2e5 and ai is from minus 1e9 till 1e9 and the input graph is a tree and the sum of n over all test cases won't exceed 2e5. So again, we are expected to solve in a time complexity of O of n log n maximum because the sum of n is still 2e5. So I'll describe the problem. Just a second. Problem E. So we are given a tree and I'll explain the problem by showing it in a tree actually. So let's just make some random tree. So what we are doing is we are doing some walk in this tree. A walk can be anything. We can start from any vertex. We can do it like this. We can go here, then we can come back. We can go here. We can go here. We can go here. So this walk will connect all these vertices. The walk I just shown. Let me just put a tick. We can go here, 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 here. Then we can come back, go here, here, here. So this type of walk we can do in the tree. And the score of this walk is nothing but for all the nodes in this walk, for all these 1, 2, 3, 4, 5, 6, 7, and 8 nodes in this walk, the score is nothing but if a of I is positive, then we multiply by 2 to the power w I. Yep, let's just do it like this. W1, W2, W3 are the weights given. So basically what we are doing is, if the weight is positive, we are multiplying by 2 to the power W1, and if the weight is negative, we are multiplying by 2 to the power minus W2, minus 2 to the power minus W2. So when the weights are negative, we are multiplying our answer by a negative quantity, right? So the thing is, in this problem is, you can obviously tell we need to try to make the number of vertices with negative weights even. We need to try to make number of vertices with negative weight even, because if we multiply this minus sign even number of times, only then it will become a plus sign, and only a positive value will correspond to a maximum value for the answer. So we need to find the maximum value of this expression for all the paths possible in this tree. So obviously we need to select some paths that have even number of negative weights, so that this minus gets cancelled out, right? So that is our problem. So let's first start by checking out the test cases. So the first test case is 1, 2, 2, 3. 1, 2, 3 and -1, -1, 2. So -1, -1, 2 are the values. So pretty easily we can see that we can just select all the three edges, so that this minus and this minus will cancel each other out, and we will have the powers all multiplied. So we will have answer as minus of 2 to the power plus 1 into minus of 2 to the power plus 1 into 2 to the power 2. So 2 to the power 4, which is 16. So again, instead of actually multiplying like this, we can try to calculate just the sum in this problem. So just calculating the sum would also be fine, since we can just take 2 to the power sum in the end. So that also we can do. The next test case is 1 to 2, 2 to 3 and 5 minus 10, 2. 5 minus 10 and then 2. Then now we see that if we take these two, then we will have only 1 minus. If we take all of these three, then again we will have only 1 minus. So we cannot take this minus in any way possible, because there is only 1 minus in this tree. So we obviously cannot take that, since we need even number of minuses. So we can either take only this or only this, and obviously since 5 is greater than 2, so we will just take only this node. So 2 to the power 5, 32 will be our answer. Then again 1, 2, and since both of these are positive, we will just take both of these, and yeah, whatever the answer comes out. Let's take this test case. It might be interesting. So let me draw it. 1, 2, 2, 4, 4, 6. 1, 2, 2, 4, 4, 6. And then 4, 3, 6, 5. 4, 3, 6, 5. And the values are 1 minus 1, 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 1 minus 1. So we see that there are 3 overall minus 1s. So obviously now we cannot take the whole tree, right? That is because if we take the whole tree, then 3 minus will come. We can take a maximum of 2 minuses. So what we can do is we can select this, or we can kind of select this, right? So I think selecting this would be the most optimal only, because we are selecting 2 minus 1s, which are the maximum number of minus we can select here, and we are selecting 2 plus 1s as well, and we cannot take this third plus 1. So yep, so 2 to the power 4, 16 will be the answer for this. Yes. So first of all, before I move on to the solution, if you guys have any doubts regarding the test cases, ask right now, because this is a little difficult question, and you guys might get lost if you didn't understand the test cases. So you guys understood the test cases, right? So, okay, I suppose you guys have understand. So, okay, so I'll move on. So basically, we kind of didn't learn much from the test cases apart from the fact that let's write down what we have learned. We have learned that we need to take paths which have even number of negative weight nodes, right? Even number of negative weight nodes. So this, we don't really have any other observation right now. We don't have. So what else can we say about this problem? What else comes to our mind? We have some ideas like this. We can try to greedily pick the maximum weights. But generally quite hard to do this because there can be several cases like this. We can say, let's say a tree looks like this. There's a huge tree and there is only 1 minus 1 here, and here we have a value of 100 and all the other nodes are 50. So what happens when we greedily select this node as our a node inside our path? So we will not be able to select any other node, because if we try to go to some other node from this node, we will include this in our path, and if we include this in our path, so this will make our whole value negative. So that would not be optimal, right? So instead of taking this 100, we will take this whole tree which has a lot of 50s, which are not the maximum, but they will give us the greatest answer. So obviously this idea fails. We cannot greedily select the maximums, right? So we need to find some way to brute force this. Our greedy ideas are not working. I don't have any other greedy idea that I could have taken count of. So we need to find some brute forcing solution. Right, we need to find some solution to brute force this problem. And generally brute force solutions, they are DP. DP is basically brute force. DP is basically brute force. So let's assume that this problem will be solved using DP, and now let's try to solve the problem. So obviously DP means subproblems, right? DP means subproblems. We need to find subproblems to our problem, and then using those subproblems solve our problem. So before we get to the subproblem part, let's just try to see what happens in a normal simple brute force. So if we have a tree like this, what can a simple brute force look like? Let's not think of how we will code it or how we will write the code for the brute force. Let's just do it on pen paper. Let's not worry about the code. So what will a brute force look like? We'll go here, then we'll come back, and basically we'll try to explore all the possibilities, right? All the possibilities. So what happens? What kind of subproblem can we identify in this kind of brute force? Let's say that I'm starting from here. Currently in my brute force, I'm on this node and I'm trying to see the all the paths that contain this node. I'm trying to find the answer for those. So what happens? What will happen is basically I will consider every path, right? And what I can see that these four are the childs of this node, right? If I mark this as the root, these four becomes the child. So what we can say that is, let's look at the subtree of this child. for every path in this new tree, let's consider this as a separate tree. Let's consider this as a separate tree. What we can do is, for every path passing through this node in this tree, we can extend it to this node in the bigger tree, right? We basically, let's say if we are calculating brute forcing for this tree, we will, the paths that we will travel overlap with the paths that we will travel in this tree. Basically, in the bigger tree, we will also travel all the paths that were included in this subtree, right? So what we can try to do is, let's say I want to find the answer for this node, like what is the maximum possible answer of a path that contains this node. So first of all, I'll need to, the observation that we made is I'll need to ensure that negative weights are even. So number of negative weights are even. So we can see that only the parity matters. Only the parity matters, right? We see that here that we just need to tell if it is even or if it is odd. So only the parity kind of matters. So if we are trying to find the, let's suppose that this node has a positive weight. This node has a positive weight. Since we are since we are fixing that this node comes in our path, so let's also fix that this node has a positive weight. So number of negative weights must be even, and only the parity matters, right? So what we can do, basically any path going from this node will be any path in this subtree, any path in this subtree, and any path in this subtree, and any path in this subtree. And all of those paths will get combined by this node, and that will be the solution for all the paths passing through this node. So how can we separate out this subtrees problem and use some quantity that we have calculated for this subtree as the parameter that we can use to calculate for this subtree? How can we use, what parameter can we calculate for these subtrees so that we can find out the answer for this pretty easily without writing any exponential brute force? So since we see that only the parities matter, right? So what we can say is we can kind of maintain two things. One, maximum sum containing odd negative weights and containing even negative weights. So basically what this is, for this subtree, let's say that I have calculated two quantities. What will be the sum of absolute, basically sum of the weights absolute values if I take negative number of if I take odd number of negative weights, or if I take even number of negative weights. Obviously I know that the final answer will be only corresponding to a root that has even number of negative weights, but a route passing through this node might, let's say is containing even number of nodes, even number of negative nodes. It might have odd number of negative nodes in this subtree and odd number of negative nodes in this subtree, which add together to cancel out and become positive for this. So basically these two values will help us calculate the answer for this node. The maximum sum containing odd negative weights and even negative weights. Positive weights, we can contain any number of positive weights. There is no constraint on that. So these two values. Now how can we calculate using these two values? What we can say is, now let's denote this as node. Let's denote this as C1, C2, C3 and C4, right? So initially I want to calculate path through node having even negative weight nodes. Very simple problem. So how can we break this problem now? So let's talk about the first child. and let's say that from the first child I have taken an odd number of negative weights. In the subtree of the first child I have taken an odd number of negative weights. So what will that correspond to? Since I have taken odd number of negative weights from here, I will need to take odd number of negative weights from the other three children's. Only then the total will become positive. Total will become even. So what we can say is we will have two cases. Case 1 we take odd from C1. Case 2 we take even from C1. So this case will correspond to path through node having odd negative weight nodes and only considering children's from C2 to C4. Basically, we have made sure that now C1 does not count. We have already fixed for C1. We only can take from C2 to C4 and we need to take odd negative weights. And the case 2 is nothing but path through node. Let's just having even negative weights and children's from C2 to C4. And now again, both of these will correspond to two different problems. One where we take odd from C2 and one where we take even from C2. And if we take even from, so I'll just write for one of them. Let's say that we have taken even from C2, then what will happen? From C3 till C4, we will need to take again even negative weights. Had we taken odd, we would have to take odd negative weights from C3 till C4 because taking odd changed our parity. We needed to take even and we had taken odd from C2. So C3 and C4 must also give odd. So this kind of sub-problem chart we can see, and we can see states forming here. We can see states forming here. So what values can we, what parameters can we give for this state for that each state to become a unique state? So first of all, we have a node. And then we have the information that do we need negative number of nodes? Do we need even number of negative nodes or do we need odd number of negative nodes? So two quantities, node, then even slash odd. And then for the given node, how many children do we need to consider? So child. So these three parameters we can write. So a simple DP can look like this: DP of node, comma child, comma even slash odd. And we can simply make two transitions from this: DP of node, comma child plus 1, and just let's just denote this as a sum variable. So if here let's say we have taken odd from the child, so this sum will invert its value. Sum just, if sum is 1, if sum is 0, then that means this is even. If sum is 1, then that means this is odd. So basically, if odd number of negative weights were taken from the child, so then from the next child we need to invert the parity. And DP of node, comma child plus 1, comma sum, if we take even. And now we will also have to add the value. So the value would be nothing but DP of child, comma child of child, starting from the 0th child of the child. So 0, 1, 2, 3, 4 will represent the 0th child, 1th child, 2nd child, and we can just fix their order by doing a DFS on the tree. So child, comma 0, comma whatever sum we have. So we had taken odd, right? So odd, which is 1, this plus this, and DP of child, comma 0, comma even, so this plus this. So these two simple transitions we can have. And to analyze the time complexity, we can see that the total number of states, although it might look like n square, but there are only O of n states, since for each node the sum of childs would be equal to n. So for I equal to 1 to n, number of child for each node equal to n. So the number of states will be equal to, here we have a multiply by 2, so 2n. And the number of transitions per state is also 2. So O of n only is this. And then our final answer could easily be just dp of each node starting from each child and the sum as even, starting from the 0th child and sum as even. So the definition is a little different the definition is not a little different, but to easily implement, I have written this state as a -1 basically, so that I can correspond to the, let me just explain that also. So what this means is -1 is the parent itself. So dp of node -1 even is nothing but dp of node comma 0th child of node and value, and this value will be determined if node had a negative weight or a positive weight. If the node had negative weight, then this will become not of even, or this will remain even if the node had positive weight, because positive weight will not affect the parity and negative will affect the parity. And also we will have to add the value of absolute of value of node, weight of node. So plus. So I think this is a little difficult problem. So don't force my implementation upon yourself. Follow this idea and the idea of this state. Even you can find solutions that actually don't require defining a state like this. You can maybe write a DFS, then calculate for all the, there are certain different implementations for this problem as well. I could think of them, but I decided to go with this. So don't force my implementation upon yourself. Just follow this idea and try to write your own implementation. And if you are understanding my implementation, then that is good as well. So you can follow mine as well. So I have denoted this -1 state as if this only has this one transition. So it isn't actually a state. It is a kind of pseudo state where I am just reducing my if elses in code. I just won't have to write a lot of if else if I use this certain parameter. This will then just straight up transition to this, which is absolute of w of node comma 0th child and value. And if the node had a positive weight, then even. If the node had negative weight, then not even, which is odd. And also the base case would be simply dp of node comma number of childs and value. So this means that the number of childs of the node has ended. So in this case, we would have been transitioned to the C5th child, which does not exist. So in this case, if value is odd, if we need an odd value, which is obviously not possible, so we will return -1e17, which denotes this case as an invalid state. And else if it is an even, then obviously we'll return 0, because we don't have any more values to select from, right? So we can only select 0 values, which is even only. So odd number of values we cannot select. So this is the base case. So I'll show you guys the code. So here I have just cleared my global variables. You will understand this. And this is nothing but I take input the val array, I take input the graph, and this DFS is a quite simple DFS. What I am doing is I am designing a tree. Basically, I do this DFS and child of, I am storing for each node what are its childs. For each node, I am storing the childs basically in this DFS. So after this DFS, I would have formed this GC graph, which for each node will contain its child. basically the input does not tell us which are the child and which is the parent. It is a direct undirected graph, so we need to define a specific order for childs and parents. We need to define a root. So I have defined 1 as the root and calculated the childs for each node. And then this is again nothing but me just setting up my DP. So I'll explain you the main part. This is the main part. So in the subtree of the node, I'll explain the state. In the subtree of the node, starting from the cnumth child, I need to find the maximum sum, given that the total number of negative weights node I am selecting is even or is odd. So that is this sum variable. Sum variable is for telling me that I need to select even number of negative weight edges or the odd number of negative weight edges, and this DP will return me the maximum sum. Actually, these both sums now sound confusing, but I just wrote it like this. I don't know why. So anyways, this DP returns the sum of all the weights of that subtree, given that there are even negative weights or odd negative weights. So if CNUM is GC of node dot size, that means if CNUM is the last, basically CNUM has run out of index. Node does not have this child. So if sum is 0, then return 0, because sum is 0 means that I need to select even number of negative weights. So I can select 0 number of negative weights, which is even, and return 0. Else if sum was 1, then that means I need to select odd number of negative weights, which is now certainly not possible. So I'll just return an invalid, a very low number, which will not affect my code because I am finding the maximum values. So now this is my way of handling my transition. So this basically -1 is nothing but I avoided writing an if statement here. What it does is basically it transitions me based on the value of weight of node. If weight of node was negative, so basically finding an even sum, if we had to find an even sum, now we will have to find an odd sum, because the weight of node itself is negative. So from its subtrees, we will also need to take an odd sum. So what I'm doing is, if the weight of node is negative, then answer will be value of the weight of node plus DP of node starting from its 0th child and taking the not sum. Basically, if we wanted to find even, then we find odd. If we wanted to find odd, then we find even. Else, if the value of node was positive, then we don't change the parity of the number of negative weights. Now this is the main code. So what happens? Answer, max of answer comma. In this case 1, transition 1, we take an even number of negative weights from child. Case 2, we take an odd number of negative weights from child. Case 3, we skip this child entirely and we don't take any weights from this subtree. So this plus, now since we have taken an even number of weights, our parity will not change. And if we had taken an odd number of weights, our parity would have changed. And if we skip this child entirely, then again our parity will not change. So these three, and this is for memoization. And also a very important thing, why did I do memoization here in this else loop? Basically 2 reasons. First of all, these are not actual transitions, these are just O of 1 transitions. So this would be same as even if I memoized, it would be literally the same. Again, this is also 1 transition. Also, since I'm using this -1 value here, memoizing this will give me a problem, because -1 nodes, -1 indexes cannot be stored, right? So again, I would have to declare this as some another number greater than, and so I just avoid memoizing here. I can just memoize here, down here, and they are literally just 1 transitions. So it doesn't really affect my time complexity much. So this will give me the answer. And for the answer, I take the maximum for each node, for every path containing each node which has a positive number of negative weights, even number of negative weights. So basically, even number of negative weights in ith subtree. So I take maximum for all the subtrees and I would get the answer. And then I just binary exponentiation 2 to the power answer modulo mod. So that was the solution for problem E. If you guys have any doubts, you can ask. I understand that this might be difficult for a lot of you, but you guys would still learn something. Even after just by listening to the solution, you guys would still learn something. So it's fine. It's fine if you didn't understand this fully or might not be able to implement it on your own, since this is a little difficult problem. Okay, so I don't think you guys have any doubts, so I'll end the live stream here. And I'll just wait for a minute more. You can ask if you have any doubts. Okay, so I'll end the live stream. Thank you.